Welcome to EPG Pathshala. Students, today we are going to discuss on gasification, a thermochemical energy conversion process. Gasification is one of the thermochemical process like combustion and pyrolysis, but they differ from the combustion with insufficient oxygen supply for the conversion of the organic fuel into gaseous products. The major products of gasification are syngas and producer gas. In India, around 150 megawatt of electricity is produced by means of gasification. In this module, we will be discussing on gasification, how it differs from combustion process, what are its advantages over that, what are the different reactions or the steps involved in gasification process, what is its mechanism, what are the different types of gasifiers like updraft, downdraft, crossdraft and fluidized bed reactors of gasification. We will also see different applications of gasification. We will be seeing what are the importance or significance of equivalence ratio in thermochemical conversion process. Let us start with thermochemical conversion. Thermochemical conversion of organic matter or organic material with atmospheric air or oxygen in presence of heat is as per the following reaction: CHXOY plus N multiplied by 0.21 oxygen plus 0.79 nitrogen is heated to produce carbon monoxide plus hydrogen plus carbon dioxide plus water plus CHXY, which is hydrocarbon, char, tar and heat, where the 0.21 and 0.79 comes from the air which is used for the burning purpose. The product formation in the above reaction depends upon the air quantity used. So, the reaction mechanism is explained clearly by means of equivalence ratio, which is abbreviated as ER or designated as phi. This ratio is represented by the formula phi is equal to air used in a reaction divided by stoichiometric air required. If phi is 0, or in other words, if the reaction is taking place in absence of air with some external heat supply, the end products are solid fuel, that is char, liquid fuel which is semi-solid, which is tar, and gases. This process is called pyrolysis, that is phi is 0, then pyrolysis occur. In this process, the chemical energy of biomass or the fuel is converted into chemical energy of gas, solid and tar. The quantity of solid, liquid and gaseous fuel depends on process operating parameters. If phi is 1 or above 1, fuel is completely burned and the end product is flue gas at high temperature. The process is known as combustion. Sensible heat energy of the flue gas is the useful end product. All chemical energy of the fuel is converted into heat energy of the flue gas. Solid fuel, tar and combustible gas are almost negligible in the products during combustion. When equivalence ratio is between 0 and 1, combustion takes place up to a point till the reacting oxygen is available. This of course will depend on the quantity of actual air supply in the process. Due to combustion, carbon dioxide and water vapor are generated in the process. Since the reacting air is not adequate, that is less than the stoichiometric value, char, tars and other gases like carbon monoxide, hydrocarbons, that is CXHY, are also formed. Due to heat energy, carbon dioxide and water vapor react with carbon to form carbon monoxide and hydrogen. The chemical energy of biomass or the organic fuel gets transformed into chemical energy of gaseous product. This process is called gasification. So, the optimum value of equivalence ratio for gasification process falls between 0.3 and 0.4. That is, if the value of phi is between 0 and 1, gasification occur. If it is 0, pyrolysis occur, and if 1 or above 1, combustion occurs. Now, what is gasification? So, we have already seen the thermochemical conversion technologies include combustion, gasification and pyrolysis. This produces energy in different forms. Gasification is the process involves converting organic fuel into gaseous product, mainly the producer gas or syngas, by supplying less oxygen than is needed for complete combustion of the fuel. During gasification, the fuel is heated to a higher temperature, which results in the production of volatile compounds, that is gases, and solid residues, which is char. Gasification is an incomplete combustion of carbonaceous fuel. It can be represented as biomass plus limited air produces carbon monoxide. You can say it is a mixture of carbon monoxide, hydrogen, methane, carbon dioxide, water vapor and nitrogen. If you see the chemical and sensible energy of this product gas, the sensible and chemical energy of these gases during thermal conversion of biomass as a function of equivalence ratio is depicted in this figure. The chemical energy of gas increases with increasing equivalence ratio and becomes maximum when the equivalence ratio is 0.24 and starts decreasing thereafter with increasing equivalence ratio. The sensible energy of gases increases continuously with increasing equivalence ratio. The total energy of the gases is sum of sensible energy and chemical energy. In gasification process, the gas needs to be cooled to remove the tar and other condensable matter before feeding into the engine. If we want to use it for thermal application, there is no removal of this tar, or you can use the sensible energy of gas. Let us see what are the advantages of gasification over combustion. Combustion of biomass is a direct and easiest process, and here the overall efficiency of generating heat from biomass energy is low. Here complete combustion, or you can say the sufficient or excess of oxygen is used up. Gasification use low value feedstocks and convert them into electricity and also into transportation fuel comparison to the heat energy from the combustion. The use of advanced technology such as gas turbines and fuel cells with syngas generated from this gasification also increases its efficiency over the product of combustion. For complete combustion of solid fuels, excess air is needed, as we have already told, and high combustion temperatures generate more NOx, nitrous oxide, or oxides of nitrogen and other emissions as compared with the combustion of products by gasification. During combined cycles where combined heat and power generation, contaminants in syngas such as sulfur and nitrogen species and trace elements are removed efficiently, resulting in much lower emissions in the case of gasification. So, gasification is advantageous over the combustion process. Let us see what are the differences between producer gas and syngas. Both these are products of gasification. If the gasification happens at higher temperature, that is greater than 1200 degrees Celsius, syngas or synthetic gas is produced. At a lower temperature, that is less than 1000 degrees Celsius, producer gas is generated. Its composition also varies. Producer gas is a mixture of gases composed of carbon monoxide, hydrogen, carbon dioxide and typically a range of hydrocarbons such as methane with nitrogen from the air. So, the composition or the percentage was is carbon monoxide accounts 18 to 22%, hydrogen 8 to 12%, carbon dioxide 8 to 12%, methane 2 to 4% and nitrogen 45 to 50%. So, the major one is carbon monoxide and nitrogen. Syngas mainly consists of carbon monoxide and hydrogen and is the product of high temperature gasification, mainly steam or oxygen gasification. It is produced mainly by coal gasification and it is a mixture of 30 to 60% carbon monoxide, 25 to 30% hydrogen, 5 to 15% carbon dioxide 0 to 5% methane. Here nitrogen is absent. In India, about 150 megawatt equivalent biomass gasifier systems have been set up for grid and off-grid projects for the electricity generation. More than 300 mills and other industries are using gasifier system for meeting their power and thermal application. In addition to that, 70 biomass gasifier systems are providing electricity to more than 230 villages in the country as per MNRE report. What are the fuel used for this gasification process? We can use coal. Biomass fuels include charcoal, wood and wood waste, that is branches, twigs, roots, etc. Agricultural residues, maize cobs, coconut shells, rice straw, coconut husk, rice husk and even peat. And another one, waste to energy gasification projects are going on to produce energy from municipal solid waste by means of gasification. So, these are the different means by which gasification is employed to harness energy. Let us see the gasification reactions. The main reactions of gasification are drying, pyrolysis, oxidation and reduction. In drying, the biomass fuel usually contain, normally biomass fuel contain 10 to 35% moisture. When biomass is heated to about 100 degrees Celsius, the moisture is converted into steam. So, this happens in drying process. It also helps the fuel to perform efficiently in the other steps. After drying, as heating continues, the biomass undergoes pyrolysis. It involves burning of the fuel completely without supplying any oxygen. As a result, the biomass is decomposed or separated into solids, liquids and gases. So, charcoal is the solid part, tar is the liquid part and flue gas makes up the gaseous part. Now, the third step is the oxidation. Here, air is introduced into the gasifier after the decomposition process. During oxidation, which takes place at about 700 to 1400 degrees Celsius, charcoal or the solid carbonized fuel reacts with oxygen in the air to produce carbon dioxide and heat. That is C plus O2 gives CO2 plus heat. Next is the reduction step. At higher temperatures and under reducing conditions, that is when not enough oxygen is present or available, the following reactions takes place, forming carbon dioxide, carbon monoxide, hydrogen and methane. During gasification, the fuel is heated to a high temperature which results in production of volatile compounds and solid residues. We have already seen this. The quantity and composition of volatile compounds depend on reactor temperature and type, the characteristics of the fuel and degree to which various chemical reactions occur within the process. The primary reactions that occur in the presence of oxygen result in conversion of fuel to carbon monoxide and carbon dioxide. These reactions are very fast and release heat, which provides energy needed to sustain the other reaction. Gasification of solid materials occur at higher temperature and produces gases, tar and ash. Generally, these reactions are carried out in presence of reactive agents such as oxygen, steam and hydrogen, which are added to the reactor to aid in the chemical conversion of char to volatile compounds. These reactions dominate the gasification process and dictate the final composition of producer gas or syngas. The secondary reactions which occur at temperature greater than 1200 degrees Celsius and under appropriate pressure conditions involve the decomposition of tars to produce carbon and gases. So, gasification is a thermochemical conversion process where fuel column is ignited at one point and exposed to the air blast, that is 30 to 40% of stoichiometric air which is required for the oxidation process. Different processes and operations occur in the gasifier reactor. We have already seen there are 4 reaction zones: oxidation, reduction, pyrolysis and drying. The sequence of reaction zones in a gasifier depends on type of the gasifier and direction of flow of fuel and air or gas. In the oxidation zone, carbon and hydrogen of the fuel are oxidized to carbon dioxide and water vapor. So, as per the first equation, C plus O2 provides CO2 plus 393.8 megajoule kilogram per mole. In the second equation, hydrogen plus half O2 gives water which is in liquid form plus 286.1 megajoule kilogram per mole. It can also produce H2O gas form. If gaseous vapor is produced, then the energy released is 241.5 megajoule per kilogram per mole, where it is adjusted with the conversion to steam. So, here the reaction 1 and 2 are the principal oxidation reaction, and these are highly exothermic reactions, and you can see the plus sign indicates the energy is released. Almost all the oxygen consumed in gasification process is used up in this zone. The temperature in oxidation zone normally range from 800 to 1300 degrees Celsius, depending upon type of gasifier and the fuel used in the gasifier. The carbon dioxide and water vapor leave oxidation zone at high temperature and move into the reduction zone. So, in the reduction zone, the carbon dioxide and water vapor are reduced to carbon monoxide, hydrogen and methane, and this is in accordance with water gas reaction or Boudard reaction, water gas shift reaction, methane formation reaction. In water gas reaction, you can see water plus carbon produces carbon monoxide plus hydrogen with negative minus 122.6 megajoule kilogram per mole. In Boudard reaction also, the carbon dioxide plus carbon produces carbon monoxide, 2 molecules of carbon monoxide with minus 172.6 megajoule kilogram per mole. In water gas reaction, the carbon dioxide plus hydrogen will produce carbon monoxide plus water along with consumption of 41.2 megajoule kilogram per mole of energy. In the methane formation reaction, the carbon reacts with 2 molecules of hydrogen to form methane along with 75 megajoule kilogram per mole of energy release. Reactions from the equation 3 to 6 are the principal reduction reactions and are reversible reactions. The temperature in the equation 3 is 900 and in 4 is 1100 degrees Celsius, and for these 5 and 6 equations or the reactions is 700 to or 600 to 700 degrees Celsius. So, it indicates that higher reactor temperature during gasification process favors higher concentration of carbon monoxide and hydrogen in the producer gas. The low reactor temperature leads to higher methane concentration in producer gas. So, unlike oxidation reaction, these reduction reactions are endothermic, that is 3, 4, 5. These reactions are endothermic and they absorb heat, that is why they have a negative value. Heat liberated in this oxidation zone of the gasifier is used for the reduction reactions. So, the gas temperature drops from around 1000 degrees Celsius in the oxidation zone to 450 degrees Celsius at the end of reduction zone. So, there is a reduction in the temperature profile inside the gasifier. Apart from oxidation and reduction reaction, pyrolysis and drying also takes place in gasifiers, as we have already seen in the different steps in the reaction. The pyrolysis takes place adjacent to the oxidation or reduction zone depending upon type of gasifier. Let us see what are the different types of gasifier. The gasifiers are usually classified on the basis of direction of fuel and air or gas flow in the reactor. Based on that, there are 4 major types: updraft, downdraft, cross draft and fluidized bed gasifiers. Let us see updraft gasifier. An updraft gasifier is characterized by a counter current flow of the fuel and air or gas in the reactor. That is, fuel is fed from the top and air is introduced at the bottom of the reactor. The producer gas exits from the top of the gasifier. You can see in this figure, the biomass is fed from the top, air is from the bottom, while the producer gas is exiting or releasing out from the top portion. The reactive agent is injected at the bottom, that is the air or whatever the reactive agent, it is injected at the bottom of the reactor and it ascends to the top, while the fuel is introduced at the top and descends to the bottom through zones of progressively increasing temperature. As per that, you have four zones in gasification reaction in the sequence: drying, pyrolysis, gasification and oxidation. Heat from the gasification and oxidation zones rises upward to provide energy for the pyrolysis and drying zones. So, you have oxidation zone at the bottom, followed by the reduction, then pyrolysis and the drying zone. Gases, tar and other volatile compounds are dispersed at the top of the reactor, while ash is removed at the bottom. The syngas typically contains high levels of tar, which must be removed or further converted to syngas for use in applications other than direct heating, because if a tar is present, its efficiency is getting reduced. Oxidation zone is formed at the bottom of the gasifier, as I told you, then the reduction, pyrolysis and drying zone. This is the sequence of the reaction or the steps happens in a updraft gasifier. So, in an updraft gasifier, the producer gas passes through the low temperature pyrolysis and drying zone in the gasifier before exit. The tar released in pyrolysis zone and water vapor formed in drying zone move along with the producer gas unconverted. Thus, the gas generated from an updraft gasifier contains high quantity of tar and moisture. The tar content of producer gas normally varies from 1 to 20 gram per Newton cubic meter. The gas is therefore considered suitable only for the thermal applications, and it is widely used. This type of gasifier is widely used to gasify biomass resources and generally use steam as the reactive agent. But slagging can be severe if high ash fuels are used. So, these are unsuitable. This type of gasifier is unsuitable for use with fluffy or the low density fuels. Downdraft gasifier, it is also known as co-current gasifier. It is characterized by co-current flow of air or gas and the fuel. In this type, normally fuel is introduced from the top, while air is fed either from the top of the reactor or from the side in the oxidation zone. Fuel and air or gas move in the same direction. The location of zones are reversed in downdraft compared to the updraft. So, the pyrolysis products are allowed to pass through the high temperature oxidation zone, where they undergo further decomposition. So, in this type of gasifier, the fuel is introduced at the top and reactive agent is introduced through a set of nozzles on the side of the reactor. Moisture is evaporated from the biomass fuel, which serves as the reactive agent. The syngas leaves the gasifier from the bottom and contains substantially less tar compared to updraft gasifier. This reduces the need for further purification, and it is more suitable for a wide variety of applications. In this type of gasifier, the pyrolysis products pass through high temperature oxidation and reduction zone before the gas exits from the gasifier in comparison to the updraft gasifier. So, most of the tars are either burnt or cracked thermally in this gasifier, and so it has minimum amount of tar, minimum quantity of tar and other condensables, and considered as best for the engine operation. Further, this downdraft gasifiers are classified as downdraft gasifier with throat and without throat, that is throatless gasifier. Downdraft gasifier with throat is also known as invert type gasifier. It has a narrow section below the air entrance point in the reactor, and it is known as the throat. Due to decrease in the cross sectional area at the throat, the air or gas velocity increases, resulting high and better temperature distribution in the oxidation zone. In a downdraft gasifier, pyrolysis zone is formed above the oxidation zone, whereas reduction zone is formed below the oxidation zone. It is highly fuel specific and operates only on wood chips, charcoal and selected woody agricultural crop residues. It has an efficiency of about 75% at full load operation. So, the downdraft gasifier with throat produces best quality producer gas, but it is not suitable for gasification of paddy husk. Since this is an important agricultural crop residue of our country having potential as an energy source, a throatless downdraft gasifier was used for the gasification of this type of material. It has a constant diameter without throat or without any narrow section. The reactions on sequence in this gasifier is similar to that of gasifier with throat. It gives a smooth and satisfactory engine operation and successfully used in the case of low density leafy biomass for engine quality gas production. So, here the zones are reduction zone followed by the oxidation zone, pyrolysis zone and the drying zone. And here the producer gas is collected from the normally from the bottom. Cross draft fixed bed gasifiers exhibit many of the operating characteristics of downdraft gasifier. Here air or air steam mixtures are introduced into the sides of the gasifier near the bottom, while the syngas is drawn off on the opposite side. The oxidation and drying zone are concentrated around the sides of the unit. It is clear from the figure. This gasifier responds rapidly to load changes, are relatively simple to construct and produce syngas suitable for a number of applications. This gasifier operate with wide variety of fuels as compared to the other type updraft or downdraft gasifier. High gas exit temperature, higher gas velocity at the gas exit, poor carbon dioxide reduction are certain characteristics of this type of gasifier. The fourth type is fluidized bed gasifier. It is a homogeneous reactor bed of some inert sand material. Usually high alumina refractory sand is used as bed material, or you can use ash or char, which acts as a heat transfer medium. This bed material is act as the heat transfer medium and fluidization is carried using air or gas. Usually ground or pelletized biomass having uniform size is used in these gasifiers. The fuel is introduced in the inert bed material. Air is introduced through an air distributor at the bottom of the bed in the reactor. The bed material transfers heat to the fuel and blows reactive agent through a distributor plate at a controlled rate. So, in this gasifier, oxidation, reduction, pyrolysis process occurs simultaneously. So, unlike fixed bed reactor, this gasifier have no distinct reaction zone and the drying, pyrolysis and gasification occurs simultaneously during the mixing process. In fluidized bed gasifier, a precise control of reactor temperature can be maintained by adjusting air fuel ratio. So, materials with high ash and low ash slagging temperature can be gasified in this type of gasifier. But you should be very careful in using a uniform and small size material as a fuel in this type of gasifier. This is characterized by high gas exit temperature, very high solid particulate matter in the gas and relatively low efficiency. The producer gas generated from a fluidized bed gasifier requires extensive cleaning for thermal as well as mechanical application. So, it has strong gas to solids contact, excellent heat transfer characteristics, better temperature control, large heat storage capacity, a good degree of turbulence and high volumetric capacity. But they operate at pressures slightly above atmospheric levels and they respond slowly to load changes. This is the line diagram which shows the fluidized bed gasifier system. Here you cannot see different zones of oxidation, reduction, pyrolysis and drying. Apart from these 4 types of gasifier, another one is entrained flow gasifier. The fine coal particles react with co-currently flowing steam and oxygen. Since the gasifier operates at a high temperature, a good conversion of about 99% is obtained and destruction of tar and oil yields very pure syngas in it. However, this type of gasifier has a high oxygen demand and also high ash content in subbituminous coal and that also increase the oxygen consumption. This type of gasifier mainly used in cold gasification. Let us compare the advantages and disadvantages of different gasifier types. We have seen the four major one plus entrained flow. What are the four gasifiers? Updraft, downdraft, cross-draft, fluidized bed and also the entrained flow. In updraft, the advantages are it has a simple design, high charcoal burn out, high fuel to gas conversion efficiency, it accepts fuel with high moisture content, it accepts fuel of different size, but it has high amount of tar and pyrolysis products, extensive gas cleaning is required if it has to use for power application. In the case of downdraft, it contains low or less tar, it is best option for usage in gas engines. At lower loads, fewer particles are seen in the gas, but it has limited scale up. At low temperature, more tar can produce, high amounts of ash, fuel requirements are strict, that means it is too specific. In the case of cross draft, it is only applicable for small scale operations, and due to high temperatures, gas cleaning requirements are less, but the high amount of tar is produced. In the case of fluidized bed, compact construction, uniform temperature profile, it accepts fuel size variation, high ash melting, point of biomass does not lead to this clinker formation are the advantages, while gas stream contains fine particles of dust, complex system due to low biomass holds up in the fuel bed, variety of biomass can be used, but fuel flexibility is applicable for biomass of smaller size. In the case of entrained flow, it is applicable to large system, short residence time is required for the biomass, but it requires high investment and strict fuel requirements. What are the operating parameters for gasifier? The performance of gasifier depends mainly upon fuel moisture content, equivalence ratio, temperature, shape and size of the fuel. The moisture content. Moisture in the biomass has a marked effect on gasifier performance, producer gas quality and gasifier efficiency. High moisture content in the fuel tend to reduce the temperature in the oxidation and reduction zones of the gasifier, resulting poor quality producer gas. The equilibrium producer gas composition from gasification of wood as a function of moisture content is shown in this figure. The best gas is obtained at a moisture content of about 15%. At lower moisture levels, the hydrogen content of gas is low and carbon monoxide level of gas decreases with increasing moisture. The practical experience indicates that moisture level of about 25% in a downdraft gasifier with throat, the gas quality is so poor that self-sustaining flame is not produced from the gas. Because of lower carbon monoxide and hydrogen content in the producer gas, gasifier efficiency also decreases at higher moisture. Apart from this, it also creates problems in smooth operation of the gasifier. The material tends to form a bridge in the pyrolysis zone of the gasifier and stops flowing to oxidation and reduction zone in a downdraft gasifier. The next parameter is equivalence ratio, which is represented as phi. It determines the air or oxygen supply to the gasifier, and in other words it is air fuel ratio. We have already seen how the phi denotes or how the phi controls the thermochemical reaction. The air fuel ratio controls the gasifier temperature and in turn the gas quality. The equilibrium producer gas composition as mole fraction of different constituents of producer gas during gasification of wood is shown in this figure. As the equivalence ratio increases, the carbon monoxide level of producer gas increases, and after passing through a maxima at equivalence ratio of 25% starts decreasing and carbon dioxide starts increasing. The methane content of producer gas decreases with increasing equivalence ratio up to this 25%. The best gasifier performance in terms of quality and efficiency is obtained at a ratio of 0.25 to 0.3. It is observed that best gasifier efficiency is obtained when equivalence ratio is between 0.35 to 0.4. It may be due to the fact that actual gasifier reactor, the equilibrium is difficult to be attained. In downdraft gasifier with throat, the gas compositions are more close to equilibrium compared to updraft and other gasifier reactors. Another parameter is temperature. Equilibrium producer gas composition is a strong function of temperature. The equilibrium gas composition as small fraction of different constituents of producer gas as a function of gasifier temperature is shown in this figure. Higher temperature account for higher carbon monoxide and lower methane in producer gas. The hydrogen content of producer gas increases up to a temperature of 1100 degree Fahrenheit and start decreasing thereafter. But at this temperature the carbon monoxide content is very low. Therefore, higher temperature is considered more suitable for gasification. Fuel size and shape. In fixed bed gasifier, the shape and size of fuel plays an important role in its smooth operation. The gas or the air passes through the fuel bed, therefore, too small fuel size will increase the pressure drop and may also cause material flow problems. The bigger fuel size will not pass through the throat in downdraft gasifier with throat and may cause flow problem. In bigger size fuel, it is also possible that some unpyrolized biomass in the interior of biomass, big piece may pass into the reduction zone, would result high tar in the producer gas. Fluidized bed gasifier operates well with uniform sized fuel, that is uniform pellets or ground biomass. Throatless gasifier operates well with materials like rice husk, groundnut shell, etc. So, it is important to have an appropriate fuel size and shape for the smooth operation of the gasifier. Gasification of biomass resources is used to produce bioenergy and bioproducts for use in dual mode engines, that is to produce power and to produce heat, steam and electricity. So, the producer gas can be burned as a fuel gas such as in a boiler for heat production or in an internal combustion engine for electricity generation or combined heat and power generation. And also the other product which is syngas. So, after the removal of any impurities such as tars, syngas can be used to produce organic molecules such as synthetic natural gas, that is SNG, methane, or liquid biofuel such as synthetic diesel by means of Fischer-Tropsch synthesis. So, the applications of gasification are thermal or power. The producer gas can also be burned directly in open air and it can be used for cooking, boiling water, producing steam and drying food. So, it can be used in a dryer. Here the hot gas after combustion can be mixed with right quantity of air to lower its temperature and to dry the things, example tea drying, cardamom drying, etc. It can also be used in kilns, that is brick kilns, firing of tiles, pottery articles, limestone and refractories. Boilers, producer gas can be used as fuel in boilers to produce steam or hot water. The same can be used for the power applications. It can be used for generating motive power to run either dual fuel engines, that is the engine which run on mixture of gas and diesel with gas replacements of up to 85% of diesel, or engines that run on producer gas alone. Fuel to electricity efficiency of gasification is much higher than that of direct combustion. So, the conversion efficiency of gasification is 35 to 45%, whereas combustion is only 10 to 20%. So, the generated electricity can be fed into the grid or can be used for farm operations, irrigation, chilling or cold storage and other commercial and industrial applications. So, apart from the application, it also has some advantages. The biomass gasifier technology is a mature technology and it is available in several designs and capacities to suit different requirements. The technology is suitable and economical for small decentralized application. It is a flexible operation that it can or it is able to generate electricity when required and also wherever it required. So, this is an advantage over the other renewable sources like sun, solar energy and wind energy. It is economically viable and also generates employment. So, students, to conclude this module, we have seen how the two thermochemical process, gasification and combustion, differ each other. The gasification, where the carbonaceous fuel is converted into the gaseous products with limited supply of oxygen, and the products of this are producer gas and syngas, depends upon the temperature at which this gasification occurs. We have also seen different reactions in the gasification process. There are major 4 steps involved in this one: drying, pyrolysis, oxidation and reduction. And we have also seen that this sequence, the sequence of these steps varies with the type of gasifier and fuel used. We have seen different types of gasifier: updraft, downdraft, cross draft and fluidized bed gasifier based on the direction of flow of air or fuel. We have seen in India around 150 megawatt electricity is produced, and we have seen different parameters involved in the gasification process, like equivalence ratio, which is most important one, which determine which type of thermochemical conversion process occur, moisture content, temperature, fuel size and shape. We have seen that this gasification process has a 35 to 40% efficiency compared to 10 to 20% of combustion efficiency in the energy production. We have seen this gasification products can be used for the power as well as thermal applications with or without purification. Thank you.